Welcome, everyone, to your very first day of Power Plant 101. Honestly, I am absolutely thrilled to have you all here. Today's explainer is really going to serve as your, kind of your high-level syllabus journey into the incredibly fascinating physics of aircraft engines. Over our time together, we're going to explore exactly how we wake up these highly complex machines and keep their internal fires burning in literally some of the most extreme environments on Earth. So get ready, because you are about to understand aviation power plants like never before. Okay, let's dive into this course roadmap. Over our next 10 days together, and for those following along, we'll be covering pages 4.1 through 444 and 5.1 to 5.17 in the source texts. We're going to tackle four main modules. Module 1 is reciprocating ignition systems. Module 2 is ignition timing and maintenance. Module 3 covers turbine engine ignition systems, and then we'll finish up with Module 4, engine starting systems. Now, before we get into the really fun stuff, let's establish the stakes here. Going by the university statute, your grading breakdown looks like this: 3 quizzes, 2 partial exams, 1 intensive workshop, and 1 final exam. And I just want to playfully but seriously remind you that the final exam carries a hefty 35% of your total grade. And yeah, it is absolutely mandatory. So I'd highly recommend maybe trading a few hours of sleep for some extra coffee during exam week to make sure you're ready for that one. Pay attention, take great notes, actively engage with these concepts, and you'll do great. I mean, just think about the sheer mechanical beauty of the absolute beasts you'll be working on, whether we're talking about the older radial reciprocating piston engines or those massive heavy gas turbofans powering modern jets. They actually all share one fundamental requirement. They must convert heat energy into mechanical energy to produce thrust. And not just a little thrust. They have to produce enough to completely overcome the drag of an aircraft in flight. It's wild. Our job is to learn how to ignite and start that entire process, safely and reliably, every single time.
So, kicking things off with Module 1, Reciprocating Ignition Systems.
This is where we learn exactly the magic of how we generate a spark inside those massive cylinders. And to do that, we rely heavily on the mechanical genius of the magneto. Basically, a magneto is an engine-driven AC generator that acts as a completely self-sustaining power source. It literally doesn't even need the aircraft's battery once it's running. And the whole magic happens in 3 vital steps. First, the engine rotates a permanent magnet, which induces current in a coil. Second, these breaker points suddenly snap open, stopping that primary current flow dead in its tracks and collapsing the magnetic field. Finally, that rapid magnetic flux reversal cuts across a secondary coil, inducing a massive high-voltage pulse. And that voltage is what physically jumps the gap in your spark plug. It's like a tiny contained lightning bolt.
But, here is a classic mechanics dilemma. When you're just starting an engine, it's turning really, really slowly. A slow-turning magneto creates a pretty weak spark. And worse, if it fires too early, the piston will violently kick back in the exact opposite direction. Definitely not what you want. So the totally ingenious mechanical solution you're going to study is called the impulse coupling. Basically, it's a spring-loaded catch-and-release mechanism. It temporarily holds the magneto back, winds up a heavy spring, and then snaps the magnet forward at a super high speed. This gives us a nice hot spark, and, just as importantly, a delayed or retarded spark that totally prevents that dangerous engine kickback.
Of course, all that intense, high-voltage energy ultimately ends up at the spark plug. And in this course, you'll learn that maintaining those spark plugs is basically an ongoing battle against extreme environmental degradation. We're going to dive into their internal ceramic insulator architecture. We'll evaluate heat range classifications. You'll even be in the workshop diagnosing fouling from carbon, oil, and lead deposits. Oh, and you'll learn the specific technique for measuring spark gap erosion using a round wire thickness gauge. Why round? Well, because a flat gauge simply won't give you an accurate reading on a contoured electrode. So the absolutely crucial takeaway here is that sure, we can generate a powerful spark, but it is completely useless if it arrives a millisecond too early or too late.
Which leads us perfectly into Module 2, Ignition Timing and Maintenance.
Because a huge part of getting that timing perfect actually happens right on the workbench, way before the magneto ever even touches the engine. We have to find what's called the E-gap, or efficiency gap. This is the exact rotational position of the internal magnet where opening the primary breaker points yields the absolute maximum rate of magnetic flux change. If your internal E-gap is off even a tiny bit, your spark will be weak. I highly recommend taking good notes on this part. Finding the E-gap requires extreme precision, and I promise you it will definitely be on your final exam. And once that magneto is timed internally, well, we have to actually mate it to the engine itself.
We don't want the spark happening exactly at the top of the piston stroke. We need it to occur a very specific number of degrees before top dead center on the number one cylinder's compression stroke. So in the workshop, you'll get hands-on experience perfectly synchronizing these systems using built-in reference marks, precision timing discs, and electronic timing lights. It's a real puzzle, but so satisfying when you get it right.
All right, get ready because here is the level up moment of the course. Module 3, Turbine Engine Ignition Systems.
We are stepping boldly into the jet age here. And the biggest mental shift you've got to make is understanding the duty cycle. Reciprocating engines, like we just talked about, require an intermittent, perfectly timed spark for every single compression stroke, just over and over and over again. Turbine engines, entirely different. They rely on continuous combustion. You only need the ignition system's high-energy capacitor discharge to spark during the initial engine startup, or maybe in severe weather to prevent a flameout. But once that fire is lit inside a turbine, it is completely self-sustaining. To understand exactly why it's self-sustaining, you have to grasp the Brayton cycle. This concept right here is the absolute bedrock of turbine thermodynamics. Unlike a piston engine where the 4 strokes happen one after another in the exact same chamber, the Brayton cycle is a constant pressure cycle. The intake, the compression, combustion, expansion, and exhaust events, they're all happening continuously and simultaneously, just in different dedicated sections of the engine. And the operating environment drastically affects the thrust generated by that Brayton cycle. To put this into perspective, just think about how thrust output literally plummets as altitude increases. Even if we maintain a perfectly constant airspeed and RPM, as the altitude goes up and the air gets thinner, the thrust output of the engine drops significantly. As future maintenance technicians, you absolutely need to understand these performance metrics. Part of your job is ensuring that the engine is capable of sustaining that continuous combustion safely, even when atmospheric pressure drops. We're also going to briefly look at the modern hardware you'll be handling out there, like the Electronic Control Unit, or ECU. Today, digital computers have completely transformed fuel and ignition metering. I mean, each ECU contains multiple microprocessors that are constantly interpreting signals like pressure and temperature, providing incredibly precise, redundant control over fuel injection and ignition. It makes the whole system highly efficient, and honestly, it's a long, long way from tuning old mechanical carburetors. Finally, we close the loop with Module 4, Engine Starting Systems. Because, before any spark can ignite any fuel, we have to physically get these gigantic engines rotating. We'll take a quick walk through the historical evolution of reciprocating starters to understand how we got here. We actually started in the terrifying early days of hand propping, literally pulling a massive propeller by hand and just praying you don't lose an arm to a cold, stiff engine. Yeah, no thanks. Thankfully, we evolved to inertia starters, and we developed auxiliary starting aids like booster coils and the shower of sparks induction vibrators to help out those weak magnetos at low speeds. But today, mostly you'll be working with modern direct cranking heavy-duty electric starters. But turbine starting? Oh, that is a whole different beast. You cannot just bump the starter on a jet engine and walk away. It requires sheer, continuous mechanical effort. The starter basically has to forcefully drive the heavy compressor section up to a tremendous rotational speed. And only when sufficient airflow is moving through the engine, fuel is introduced, and ignition is finally achieved, actually only then can the engine start to self-accelerate. If the starter drops out even a second too early, you'll have a very expensive aborted start on your hands. To achieve that immense torque, large commercial jets mostly use air turbine starters. These are incredibly high-powered pneumatic devices, but they need highly compressed air to spin. So where do they get it? Well, they can get it from a massive hose hooked up to a ground cart, they can cross-bleed compressed air from another engine that is already running on the wing, or they can use air from the aircraft's own auxiliary power unit, the APU. We're actually going to spend a major portion of Day 8 completely breaking down these pneumatic systems. So yeah, that is your syllabus roadmap. We have an incredible 10 days ahead of us. To wrap up today's explainer, I want to leave you with a provocative thought. Consider this a mock preview question straight off your upcoming Quiz 1. What speed does the magnetodistributor rotate relative to the engine crankshaft in a 4-stroke engine? Is it the exact same speed? Half speed? Double? Think about the physics of a 4-stroke cycle tonight. Try to figure it out before Day 2, and get ready to master this material. Have a great day, and I'll see you all in the next class.